pre-trained network have always been very helpful in multiple computer vision tasks. In this video, we are going to use the pre-trained ResNet50 in combination with the Vision Transformer to build the ResNet50 ViT. Hello friends, this is Nikhil Tomar and you are watching Idiot Developer. Please make sure to subscribe the channel to support me in my mission to make such awesome videos. So now first of all, let us understand what is Vision Transformer. So here is a block diagram of the Vision Transformer. So in simple word, we can say Vision Transformer or ViT is a transformer based architecture used in the field of computer vision. It is directly inspired by the use of transformer in the NLP task. So how it is different from a normal CNN? In normal CNN, a complete image is taken as input, while in ViT, the image is first divided into equal size patches, then they are passed through some linear layer, then we add a position embedding. After that we add an extra learnable embedding or token, and then we give that to the transformer encoder. So in this video we are going to take the advantage of both the pre-trained CNN network, that is ResNet50, and the Vision Transformer. So here I have a simple block diagram for you to understand how we're going to proceed in this video. So first of all, we're going to take our input image of this specific size, that is 512 by 512. Now I want you to just take a careful look at those shapes, how we move forward. And this input image is passed to the pre-trained ResNet50. From there we get an output of the shape none. Here none refers to batch size. So batch size by 16 by 16 by 2048. So 2048 refers to output number channel or output number of features. Then this output is passed to a convolution layer, and it transforms the number of features, the output channels, to 768. After that we reshape that output by multiplying the height and width of the feature map. Okay, after that we add the position embedding into this reshaped output, and it gives us the same dimensions, that is none 256 by 768. After that we add a class token, and here the size became none 257 by 768, and this size tensor is given to the transformer encoder. So this is how we're going to proceed in this video. Now let us try to implement this in the TensorFlow framework. So I have also built some previous two videos on the ViT, where in one video I have implemented ViT from the scratch, and in second video we have used that ViT for image classification task. So first of all, let us import all the libraries and the functions which we require. So here first we have imported the OS library, and this, in second line we have this os.environ. Here we set this value to 2. This is just to make sure that we don't get those TensorFlow messages. After that we have imported the TensorFlow, then we have imported all the layers. Here star refers to all the layers. After that we have imported this model class, which would take the input and output of your architecture and give you a model. And at last we have imported the pre-trained ResNet50 architecture. So let's start with our main class, main function, not the class. Main statement if name equals to main. So first of all we're gonna have the configuration. Okay, so this is the configuration. So this is the configuration for the base ViT, which has 12 layer. Hidden dimension would be 768, MLP dimension would be 3072, number of head would be 12, and a dropout rate of 0.1. And after that we have some hyper parameter, that is the input image size. So image would be of size 512 by 512. Then the patch size, so we want a patch size of 32. So just remember, the patch size should be such that when you divide the whole image size, that is 512, that is height or width, by the patch height or width respectively, it should give 0 as the remainder. There modulus should be 0. Just remember that. Okay, so this is a basic rule, because a patch size would be like either 1 or 0. It cannot be a floating point. If some value left, it would not be really good. So just remember, your input size divided by the patch size should give 0 as a remainder. Now next we comes to number of patches. So there's a formula for number of patches, that is image size, or we can simply say that, okay, I'll write the formula here for you all. So num patches, okay, equals to height of image multiply height of, okay, height of image multiply by the width of image, then we divide them by the patch height and width. So this is a simple formula. Here we say raised to the power 2 because image size, here both height and width are same for both the image and the patch. That is why we have raised to the power 2 here. Number of channel in the image would be 3 and number of output classes would be 10. So you can change those hyperparameter accordingly. Now we're going to build our ResNet50 ViT. So let's define a function class here, ResNet50 ViT. And we're going to provide this config dictionary to the model. Now let's build this function ResNet50 ViT and this config as CF. So first of all, we're going to have our input layer. We're going to call it inputs. So this is the input layer and it take your shape, that is height, width, number of channel of the input image. Because here this image is input is going to the ResNet50. So we don't convert this image into patches and then flatten them. No, that we are not going to do that. That we do in the plain vision transformer. So we're going to use this configuration library. We're going to say image size, then CF image size, because both height and width of image are same. So that is why we have same value here. Then number of channels. So this is the input layer and the height and width. Let me just write it here. It will be much better. That is 512 by 512 by 3. Okay. This is, we can also print it just to be sure. I'll print the shape of most of the tensors while working on this tutorial. This is just to show that we get the appropriate size and we also know how the input image is being transformed when it passes through different layers. So here you can see the input image is of size, that is none refers to batch size 512 by 512 and 3 as the number of channels. Now let's call our pre-trained ResNet50. So let me just write some lines here. Input layer. Then we have our pre-trained ResNet50. So we will call pre-trained ResNet50. ResNet50 equals to ResNet50, and inside this we're gonna say include top false. We do not want any classification head on the top of this feature extractor network. We just want the feature extractor. After that we're gonna call the weights, because we want a pre-trained network. That's why we say weights as ImageNet. After that, the input we need to provide to this network should be input tensor, and that will be this input layer which we have defined here. So we are done. Now we need to extract the output from this. So we're going to say output is equals to ResNet50 dot output. So now let us print the shape of this output layer. Let's run the program and see. So here you can see we have an input tensor of size 16 by 16 by 2048, and that is what we have in our diagram. So we have reached up to this stage. Now we need a convolution layer and then we are going to reshape it. So let us just copy this shape and put it after the code here. Now we know how our input image is being transformed. So after that, here we're gonna work on the patch embeddings. So we're gonna call patch embed conv 2D. First number of output feature, that would be hidden dimension. Then we need kernel size, that would be patch size. After that, padding, that would be same. So this is the convolution layer. Now we're gonna give the input, and the input would be the output of this ResNet50. Now let me print this patch embedding. Let's run the program and see the size. So here you can see the number of output feature are now 768. So let us copy this and paste it here. Now we need to reshape it. So we already know the size. So what we need to do, we need to reshape them. Okay, we need to multiply those height and width. But we can say patch embedding equals to reshape. So here we need the height and width. So what you can do, we can simply say it like this: underscore, then height, then width, then you can say f. Okay, and we can say patch embedding dot shape. So this is the shape. So this blank here refers to the batch size, and we do not need that. So here we can say height into width by f, and then patch embedding as the input. So this is going to reshape this patch embedding. Now let's run the program. Here you can see we have resized this tensor to this specific tensor size. Okay, so let me put the size here manually, none, 256, and the output feature 768. Okay, so we are done with the patch embedding. Now comes the position embedding. So for position embedding, we need, what we need is number of patches. So first of all, let's print the number of patches here. How many number of patches we have? We're gonna need to know that num patches. So I hope you know the formula. So according to the formula, I think they should be 256. Yeah, you can see 256 value printed here. So those are the number of patches. So first of all, we're gonna have a simple list, or you can simple tensor with starting from 0 to 2 to number of patches -1. Okay, that would be TF range. So here we're going to use TF range, not directly range, because we are working in TensorFlow, so we cannot use the normal Python functions. Limit would be CF num patches and delta, that is step, would be 256. Now I'm going to print the positions. Just see on the screen, what do we get? Here you can see we have a simple list, so it's gonna be a simple one-dimensional position embedding. Here we don't use any unnecessary difficult, just simple. That is what also used in the Vision Transformer. You can see it start from 0 to 255. So its length would be equals to number of patches. So we can say this is equals to 256. Now we have positions. We need position embedding. So that would be embedding layer. First of all, we need the input dimension. That would be equals to number of patches. Then we need output dimension. Oh, it should be output. Out. Then CF, the number of output dimension would be hidden dimension. then the input would be position. Okay, so let's print this pose embed. Here you can see it's of size 256 by 768. Now what we need to do is we need to add, that is patch plus position embedding. So we can say embed is equals to, we can copy it, patch embedding plus position embedding. So here we have both the information, the patch information from the output of ResNet50 and the simple position encoding. So let me just print the shape of this embed. We need to know how our input is being transformed. So it remains the same as none by 256 by 768. Okay, so we have this embedding. Now what we need to add a class token. So now you're gonna ask question, what is the need of class token, or what is class token? So let's go to the original ViT diagram. So here you can see we have 9 patches here and they are in a sequence. So we add positional information to them, that is 1 2 3 4, okay, till 9. So why do we need this extra patch embedding? Because at last we wanna do image classification. So in the original paper, what they have done is they have added this extra learnable embedding, and this, the output of this embedding would act as the input for the MLP head. Okay, we cannot use output from any of the patch embedding, otherwise we would be biased toward a specific patch and that would not be good. Okay, that is why we add this patch token. Now we're going to write the code for this class token. This class token is a simple thing, it's not much complicated, so don't worry about it. We're going to build a Keras or TensorFlow layer, naming it class token. So this would be a subclass of the layer class. Then we're going to have the initializer, that is inet self, and then we need to write this statement super, because we are using this parent class to build our child class. Then let's write the two simple function to implement a layer. First is self input shape. In this build function we're going to define all the weights and the variables. Then we have call function where the actual processing happens. Okay, so the weights which you have defined in the build would be used for the processing in the call function. So first of all we need to define the weights. So to define a weight we need an initializer. So here we would use tf.random normal initializer. Instead of random normal you can use 0 1 or anything, it's up to you. I'm using this random initializer. Then next we need to define the weight. Okay, so this is basically the class token. We're going to transform this class token in this weight into the class token. So it is tf.variable, then we set the initial value to 1 by 1 and then input shape. So if you see our tensor, its last shape is 768, so that is why we say input shape -1. Okay, then it should be of float 32 and we want it to be trainable as specified. Here you can see it is trainable, it is learnable. If you see, so learnable refers to that it should be trainable over the time. Okay, so now let's work in the call function. So first of all we need the batch size from this input. So we're gonna say batch size, because batch size can be a dynamic thing. Okay, it can change Like let's say you are having some batch sizes, but at last the batch size can change, so this value is not always fixed. Okay, so that is why we're gonna extract it from the input. Okay, then we need this last dimension, so we're gonna call it hidden dimension, self w dot shape -1. Now this is our class token basically. So we're gonna use tf.broadcast2 function. Broadcast underscore 2. So this is gonna take this weight, the variable, and transform it into specific size. First would be batch size, then 1, then hidden dimension. Okay, so we have this class token. Now we're gonna change its data type. So the data type should be same as the input data type. So we are done with the class token and we're gonna give it back. So let's now move to the bottom. So now we need to call our class token, and okay, here we are. So we're gonna say token class token. So this is the class. We're gonna give it the input, that is embed. So we are just giving the input just for the sake of shapes and the batch size. Otherwise we don't need. Now we need to concatenate it. Here we're gonna call the concatenate layer. And so the token, just see the diagram, is added at the front. Okay, and after that begins the path sequence. So first token, then embed. Okay, so I'm gonna print the shape of the token, not the token, the final output, that is x. Okay, so there is some problem here. Okay, we haven't specified the axis. Okay, you say, so this is the problem, input with matching shape. So some problem is with the, so we need to specify axis, that is 1. So we need to append this first axis to here. Let's do it. Yeah, you can see it transformed from 256 to 257. So we have added that learnable token here. Now comes our transformer encoder. So here we're going to build a function called transformer encoder. So let's go above and build a function called transformer encoder. Let's go for small. So it's your choice. The name can be capital, small. So it's going to take the input, then the configuration file. Not the configuration file, the configuration dictionary. So now let's have a look at the diagram. So this is the encoder block we want to build. So first, the input, the patch embedding, we have a skip connection. So first we need to save this. Then we have layer normalization. So let's implement these two steps. So we're going to say skip 1 equals to x. Then we have layer normalization. X. Next we have this multi-head attention. Now let's implement this. So the multi-head attention is already implemented in the TensorFlow. So we're going to use that one only. So just write it down below. If you want a video on multi-head attention also, I'll make a separate video and I'll try to implement it from scratch in the TensorFlow. So inside this, first we need to provide number of heads. And here we're going to use our dictionary, that is cf config num heads. Next we need key dimension, that is hidden dimension. Then we're going to give input to this layer, that is x 2 time. After that we add the output of multi-head attention and the first skip connection. So let's do that. X and the skip 1. So we are done with this part. Now next, again we have second skip connection followed by normalization layer and an MLP. Then we add them. So let's do this. X equals to skip 2. Then we have a layer normalization. We're going to copy the above line. Then we have an MLP. So we are going to define this function, that is this MLP. But for now, let's assume it's there and it's working. Then we're going to have this add, that is X, the output of MLP, and the skip 2. Okay, and we're going to give this X back. Now it's time to define this MLP function, or MLP, that is, MLP refers to multi-layer perceptron. So just two dense layer and a GLU activation and some dropout layer. So we're going to have a dense layer. Number of output feature would be hidden MLP dimension, and activation would be GLU. Input would be X. Then we have a dropout here. Here we need to specify the dropout rate, and the input would be output of dense layer. And again we have a dense layer after that. Now here number of output feature would be equal to hidden dimension. And here we do not provide any activation function, just the number of features. Then again we have a dropout. I'm going to copy it and paste it here, and we're going to give the X back. So we have defined the transformer encoder and the MLP. Now this transformer encoder is repeated 12 times, that is up to number of layer. So here we're going to use a loop, a for loop. So this loop is going to repeat up to number of layer times num layer. So input would be X, this, and the output would also be X. I'm going to call this transformer encoder. X as the input and our dictionary. Now we're going to print the shape of this X here. Let's run the program and see if we have any error or anything. Okay. See, I've done a mistake here. I've done the reverse thing. It should be skip 2 equals to X. And what I've done is reverse, just X equals to skip 2. Okay. So these are normal errors, just don't worry. At last the main thing, your program should run. Okay. So we have this shape as the output. Now this transformer part is done. Now we need to add this MLP head. Okay, let's work on that. So first of all, we will have a normalization layer. Okay, so now you remember we have added this class token. So we are going to use the output of this class token as the features for a classification. So this is added at the beginning of the batch sequence. So let us extract this. So here if you see, we have three shapes. Okay, first is batch size, number of the sequence, number of tokens or everything, then the number of features. So we need to extract from here. Okay, so we're going to say simply X. We're going to slice here. So first batch size we do not want to touch, just this. Then at 0th position we want. So the first thing we want, first feature, and the last feature we also don't want to touch. So let me print its shape. I hope you get it. Like what I'm doing here, I'm just extracting the output of this class, of that class token. You can see none by 768. Now simply we need to add a dense layer here, and that dense layer would be number of classes, and activation would be softmax, as we have more than one class. So if we have one class, you can use sigmoid as the activation function. Now we have, see, we have this input and we got the output at the end. Okay, so our ViT cycle is complete. Now we need to build the model. We're gonna give it the inputs layer, then the output X, and we're gonna give this model back. So we're gonna save this program and finally we're gonna run it. Here we have the complete architecture. Okay, so let's go to the beginning and see how it transforms. See the input shape first. That is really important. Okay, so input shape is 512 by 512. Then here we have this pre-trained ResNet50. So I think you can use any other network also, but ResNet50 is really famous. I think that especially the residual network makes the performance of the ResNet50 really good. The residual block and the residual connection. And okay, so this is residual connection. This is the ResNet50, and we have some transformations also here. You can see. And finally at the end we just take our class token features and we get the number of classes. So this is all about the ResNet50 ViT. So this is much more better than the ViT from scratch which I have built in the previous video. And in the next video I'm going to use this network for the image classification. Okay, and I believe this is going to be much better in terms of performance because it has this pre-trained part which is already trained. So it's gonna have much better features. So I hope you have enjoyed this video. If you have any problem, any question, any query, just put it down. And the code for the link for the code is in the description. So please make sure to subscribe the channel at the end. So thank you. Have a nice day.